let's see some examples of this just to make it more concrete. So one example is that this linear function 2n is big O of n squared. Why? Well, in order to demonstrate that this is true, I need to use the definition and find some constant c and some n0 such that n is less than or equal to n squared. Well, that will be true since 2n is less than or equal to 2n squared for all n greater than 0. So when n is 1, both sides are 2. And then as n grows, this side is obviously larger. Okay? So this is how you would prove this, I guess, or demonstrate that this is true. We'll also have another example. So your second example is that the exponential function 2 to the n is big omega. So big omega is our notion of greater than or equal to, of, for example, n cubed. In this case, you might need to find some number n0, such that this is true. Because for the first few, it's going to be not the case. So we can make a table of n, 2 to the n, and n cubed. And for n being 0, 2 to the n is 1, n cubed is 0. For n being 1, 2 to the n is 2, and then n cubed is 1. And I'll put one more. In this case, we have 2, and 2 to the n is 4, whereas n cubed is actually 8. Does everyone agree? So in this case, we have some inputs where the function itself is actually less than the other function. 2 to the n is less than n cubed for n being equal to 2. And this will be true for a few more as well. But once you get up to 10, okay, I'll write one more. For 3, this will also be true. 2 cubed is 8, whereas 3 cubed is 27. So we have some period of crossover, but eventually if I get to n equals 10, then this is 10, 24, and this is 1,000. And so there does exist some n0 that this is true. Obviously, the exponential function is going to grow much faster than the cubic function. So this is true because we've just demonstrated 2 to the n is greater than or equal to n cubed for all n greater than or equal to 10. Okay. So that's how you would go about proving these statements and thinking about big O and big omega.